Hi everyone. I hope you had a short break and you had a nice vacation for Christmas. But now let's get to work before the New Year's. Here we go. Okay, so we'll first take a look at the big picture. Here it's a quite nice situation over Europe. I'd say quiet across most of the parts of Europe. We have a ridge here, and then here is a really deep trough with a cyclone bringing us some really cold air and some moisture, so there is snow, and I will show you that there really is snow. Right now we cannot see it at the Airmass RGB. Also there is some cyclonic activity here above Iberia and Northwest Africa, some convection and not too strong. And in most of the Europe, it's actually some warm air still hanging on by a thread, I would say, and bringing really stable conditions to these parts. Also, if you take a look here, you can see it's really dry in these parts to the southeast of the region, while to the north we have really strong cold advection coming in. So let's take a look at some more details, because here in Airmass we cannot see too much about the cloud structures, so we will go further. Okay. Here we have two products. It's fog and cloud RGB and cloud face RGB. As I said, here on the east there is a big cyclone bringing snow, and please take notice that snow can be in really different shades of, let's say, light purple here on the east, and then to really strong blue color, as you can see on the Alps and here on the Balkan area. Also, we can really nicely see the low clouds that were almost invisible in the Airmass RGB. And also you can see the low clouds and fog here over the British Isles and France and going to the northern Atlantic. Also, the structure here to the north is open cells formations in cold air mass, convective formations in the cold air mass. And what else? Yes, so here in cloud face RGB, you can distinguish the water clouds. Here they are white, then with a little bit bigger droplets and a bit higher clouds here. And then in blue color, you can see the ice clouds. So let's go further. Even more details could be seen then in a cloud type RGB. This is not from today. This is from 3 days ago. It's maybe a little bit tricky to get used to all of the colors. So you can always take a look at the cloud type RGB guide in EUMeTrain web pages, and then train your eye to see all the details. But now I will give you just the basics. So the blue color is for the water clouds, low water clouds. And you can see here some convection forming, so you can see how it turns to green color. That indicates ice crystals, and as the clouds rise, you can see the change in color. It turns from green to yellow because it's in a higher altitude than the greenish color, and then it's a drier atmosphere. Here on the southeast side is really high clouds, thick, it's the yellowish, and then you can see here reddish color, it's then thin cirrus clouds. So the only let's say, fishy clouds are these clouds. By the structure and the color, you can deduce that it's water clouds. However, you can see that they are above these low-level clouds. So it already indicates mid-level clouds, and we want to know if there is a possibility for supercooled liquid, supercooled water droplets. Then we take a look at the infrared 10.5 and use a special brightness temperature to color the clouds. And as you can see, those clouds are really cold. So if they are liquid, then you can deduce that the liquid in there is super cooled and can form, let's say, icing if the planes go through it. Okay, that's all from me. So Dunja will take over.
Well, Kristina is a forecaster. I'm also a forecaster, and I will, in this second part of Weather Briefing, look back at some synoptic situations that were common at the end of November and in December over Croatia and part of Middle and West Europe. Well, I believe you will agree with me, especially if you are forecasters, that forecasting the fog and duration of fog is very demanding and also very frustrating. But as we know, fog and low clouds are characteristics of stable weather in the cold part of the year. And here you can see this is the one of that situation from, this is the view from my window in the city of Zagreb, the capital of Croatia, foggy and very low clouds. And this is the mountain above Zagreb, Sljeme. And it's a nice sunny weather with a sea of fog and low clouds. In this situation, during a stable situation, well, in the lower level, we had very often high pressure or non-gradient field of high pressure. This circle is the position of Croatia. And in the upper level is ridge of geopotential height. And this is the very common situation. More than a half of December, we had weather in the influence of that kind of synoptic patterns. And radio sounding shows also existence of a very strong temperature inversion. And of course, with very, very weak wind at the lower part of the atmosphere. This is the synoptic situation, and with the help of new RGBs from FCI, we can tracking fog and low clouds much easier than before. Let's look at the True Color RGB. Here you can see, this is Croatia, and I zoom it a little bit. Well, this is Croatia, this is Hungary, and you can see fog and low clouds in white color and smooth surface over continental part of Croatia and over Hungary. And also we have here in Po Valley, this is Italy, and this is Po Valley, and some low clouds or fogs are also over Adriatic Sea. Here we can notice different shade of white color, and after sometimes we will notice what is this, and here also we can nicely recognize a snow over Alps, and this blue or greenish or dark brownish color shows cloud-free area of land and sea, like it is in nature. And this is the name of the RGB, the true colors. Yeah. Unfortunately, this RGB is daytime image only, and we don't have, for example, information about cloud height. But we can move further and look. Let's look at the cloud phase RGB. From this RGB, we have information on phase, I mean water or ice, and we have additional information about the particle size. We can, in this RGB, this yellowish and pinkish, this yellowish and this pinkish color is for water clouds with small or larger particles, I mean water droplets. Then this bluish color, this is Italy, and this is bluish color is for ice particles, ice clouds with small particles. And also we can notice this, let's say, royal blue or strong blue color, and this is for snow, which is covered the Alps and also some mountains in Bosnia and Herzegovina and Crna Gora. The next one is the cloud type RGB. And now finally we can, well, this RGB is very good for cirrus clouds detection, for example, also for discrimination of snow and ice on the ground, and for detection of, for example, supercooled water droplets. Kristina showed us some example. In our case, we can recognize this red color in this in Po Valley, which means that there is a high cirrus clouds. For example, over Hungary and Croatia, this blue or turquoise color is the low-level water clouds, and this yellowish color is thicker ice clouds. We can see also some yellow dots here. This is some sign of convection over this part of Italy. And of course the snow. Yes, the snow is here in green. Snow on the ground is green. And the green dots are also here, which is also snow on the ground. As Kristina mentioned, this color of snow on the ground can be also yellow, but here it's this is green because it depends on the if the atmosphere above is humid, then the color is green. And at the end, just when we look at all three images, we can have a better information about the physics of clouds, the particle size, the temperature of the clouds, and then especially when you compare it, it's look much better than the let's say old ones RGB. And if you, as Kristina already mentioned, if you want more information about RGBs and colors, go to the EUMeTrain web page, and there you can find the quick guides where you can then it helps you for interpretation of colors on the new RGBs. Well, that's all for me. Thank you very much.
Hello everyone from my side as well. I hope you can see my screen. So Dunja already mentioned the persistent fog conditions that have been ongoing for quite some time now, and I just wanted to highlight the use of the Night Microphysics RGB. So during the day you have pretty much a wide range of RGBs available for you to see and observe fog and formation and dissipation. However, during the night, you have to stick to the infrared, the thermal channels, and there you don't have so many options. But one of the better ones is the Night Microphysics RGB. And this is an image from yesterday at 12 UTC. And this is the old Night Microphysics recipe. I say old because relatively recently the VMO or the RGB expert workshop took place, and they decided on some changes to the traditional RGBs. And so the old one, you can see in this sort of pale brownish, yellowish, orange color, the fog and low clouds. But now the new recipe has a really simple change. And you can see here the new recipe with the main change in the green color beam. And it really looks like a very different RGB compared to the previous one. It's brighter all around. You can also see some differences in the very high clouds, but the most important one is how prominent the low clouds and fog appear in this RGB. So if you go to the recipes, you can see that the recipes are pretty much the same. The sensors on the Severi do have a little bit different wavelengths. So we have the 12.0 and 10.8 and 3.9, and now we have the 12.3, 10.5 and 3.8. But the recipe itself is only changed in the green beam, in the 10.5 and the 3.8 difference. And that is because this is the main part of the RGB where we are highlighting the low clouds and fog. So with this shift towards lower temperature ranges in this difference, we are actually trying to maximize sensitivity to the fog and low clouds. And a little bit about this RGB, as probably most of you know, its primary use is the nighttime detection of fog and low clouds, of moisture boundaries in cloud-free areas, and sometimes you can use it for the nighttime dust detection, although the dust RGB does a fairly good job at that, with the main limiting factor being the twilight conditions that affect it negatively due to the solar radiation, and that is due to the 3.8 channel that is a dual channel with both infrared sensitivity and the reflectance sensitivity as well. So during the twilight, all clouds in these RGBs appear magenta. And now why did the experts decide to shift this recipe? Well, obviously, the sensors itself uses a little bit different wavelengths, but primarily because they decided that the detection of fog and low clouds is a priority in this RGB. So they are trying to maximize the sensitivity. So the dynamic range in the green beam is still 10 Kelvin, but with a different threshold. And the slightly negative differences in the green beam are now enhanced. So you have the better fog and low cloud detection, and the higher positives are now saturated. So that is the shift from the plus 10 Kelvin to the plus 6. And here is one example with the same sensor. So this is the FCI with the old recipe. And now if we switch to the new recipe, you can see that the areas with very thick fog are nicely seen with both recipes, although obviously the green becomes more apparent with the new one. But you can see also some areas like here and here where the new recipe really shows fog in places where you wouldn't really notice them previously. And now if we compare it with the old instrument, with the Severi, you can see both the spatial resolution differences, and then you bring the new recipe here as well, and you can really see the fog and low clouds much more nicely. And although, well, as with any RGB, you gain some and you lose some. So here, one of the more prominent effects of the recipe change is the 3.8 noise. So in the very cold clouds, this is a known issue in the Night Microphysics RGB, you have this greenish spots. You can see here in the old recipe, there's only a few of them, but with the new one, with the changed thresholds in the green beam, you can really see a lot of this 3.8 noise. So definitely it's not an RGB that you would use for nighttime convection monitoring. Maybe you would prefer to use something like the single enhanced infrared channel that Kristina showed in her talk. So that is it from my side. Thank you, everyone.